February 18, 1943, 2:45 in the afternoon. Above Seattle, Washington. The second prototype of Boeing's revolutionary B-29 Superfortress erupts in flames at 8,000 feet. Chief Test Pilot Eddie Allen, considered the dean of American test pilots, struggles to control the burning giant as fire consumes the port wing spar. 3 miles from Boeing Field, the massive aircraft crashes into the Fry meatpacking plant, killing all 11 men aboard and 18 workers on the ground. In boardrooms across Washington, D.C., military leaders question whether the most expensive gamble in American history has just become the most expensive failure. They called it too heavy to fly. Critics argued that no aircraft weighing over 100,000 pounds could achieve the performance specifications demanded by the Army Air Corps. Boeing's own engineers expressed private doubts about whether their revolutionary design could overcome the fundamental laws of physics. The Wright R3350 engines overheated catastrophically. The pressurization system leaked. The remote gun turrets malfunctioned. Of the first 96 aircraft delivered from the factories, only 16 were rated as flyable. Yet within 2 years, this same aircraft would end World War II with just 2 missions, forever changing the nature of warfare and human history. The story of the B-29 Superfortress begins not with victory, but with desperate necessity. By 1939, military planners understood that future wars would be decided by the ability to strike enemy homelands across vast oceanic distances. Existing bombers like the B-17 Flying Fortress possessed maximum ranges of 2,000 miles, insufficient for operations across the Pacific. The Army Air Corps needed an aircraft capable of carrying massive bomb loads over distances previously considered impossible for any flying machine. The strategic imperative became urgent as war clouds gathered across Europe and Asia. Military intelligence revealed that potential enemies were developing bomber aircraft with intercontinental capabilities. German engineers were designing aircraft capable of reaching American industrial centers from European bases. Japanese naval aviation demonstrated the ability to project power across thousands of miles of ocean. American military leaders realized that defensive strategies based on geographic isolation were becoming obsolete in an era of advancing aviation technology. Boeing had been working on advanced bomber concepts since March 1938, evolving through a series of increasingly ambitious designs. The Model 334 featured experimental liquid-cooled engines and tricycle landing gear. The Model 334A incorporated a circular fuselage and single vertical tail powered by Pratt & Whitney radial engines. Each design pushed the boundaries of existing technology while addressing the fundamental challenge of achieving unprecedented range and payload capacity. On January 29, 1940, the Army Air Corps issued specifications for a hemisphere defense weapon that seemed to violate every principle of aeronautical engineering. The aircraft would require a combat radius of 2,700 miles while carrying a bomb load of 2,000 pounds. Maximum speed must exceed 400 miles per hour at 25,000 feet. The bomber would need pressurized crew compartments for high-altitude operations and defensive armament capable of protecting against fighter attacks from any direction. Most challenging of all, the aircraft had to be operational by 1944, giving designers less than 5 years to solve problems that had stumped engineers for decades. Boeing submitted their Model 345 design on May 11, 1940, competing against proposals from Consolidated Aircraft, Lockheed, and Douglas. Boeing's concept featured revolutionary innovations that critics immediately declared impractical. The laminar flow wing design promised exceptional efficiency, but required manufacturing tolerances never before achieved in aircraft production. The pressurization system would maintain sea-level atmospheric pressure at altitudes above 30,000 feet, technology that existed only in theory. Most controversially, Boeing proposed remote-controlled gun turrets operated by gunners seated inside the pressurized fuselage rather than exposed positions. Boeing received a contract for 2 prototypes on August 24, 1940, expanded to 3 aircraft in December. The order was extraordinary not just for its technical ambition, but for its scale. Even before the first prototype flew, the Army Air Corps ordered 14 service test aircraft and 250 production bombers in May 1941. By January 1942, the production order doubled to 500 aircraft. Military leaders understood that if war came to the Pacific, the B-29 would be America's only weapon capable of reaching Japanese industrial targets from distant island bases. The first B-29 prototype made its maiden flight on September 21, 1942, with Eddie Allen at the controls. Initial results exceeded expectations. The unarmed aircraft achieved a maximum speed of 368 miles per hour and demonstrated a range of over 5,800 miles. The pressurization system functioned flawlessly, maintaining comfortable conditions for the crew at altitudes where other aircraft could not operate. Most importantly, the remote gun turrets proved the concept of centralized fire control, allowing gunners to engage multiple targets simultaneously from protected positions. However, serious problems emerged immediately. The Wright R-3350 duplex Cyclone engines suffered chronic overheating that caused frequent fires and mechanical failures. The massive 18-cylinder radial engines produced 2,200 horsepower each, but generated excessive heat that existing cooling systems could not dissipate. Engine fires became so common that crews nicknamed the aircraft the Flying Torch. The complex engine management systems required constant attention from flight engineers, who struggled to balance power output against thermal limitations. The engine problems stemmed from fundamental design flaws in the turbo-supercharger system. The Wright engines featured 2 sets of cylinders arranged in a duplex configuration that created uneven heat distribution. Cylinder head temperatures varied dramatically across the engine, causing thermal stress that cracked components and ignited fuel vapors. The magnesium crankcase, chosen for weight reduction, proved vulnerable to catastrophic failure when exposed to extreme temperatures generated during high-power operations. Carburetor icing plagued high-altitude operations where temperatures dropped far below freezing. The complex fuel metering system could not maintain proper mixture ratios across the wide range of operating conditions encountered during long-range missions. Spark plug fouling occurred frequently due to incomplete combustion at high altitudes, requiring engine shutdown and restart procedures that stressed mechanical components. Most critically, the engine-driven hydraulic pumps failed regularly, leaving aircraft without power for landing gear, bomb bay doors, and flight controls. Wright engineers worked frantically to solve the reliability problems, while production schedules demanded immediate solutions. New cylinder head designs incorporated improved cooling fin arrangements and better heat dissipation materials. Modified carburetor systems included alcohol injection to prevent icing during high-altitude operations. Enhanced ignition systems featured dual spark plugs and improved timing mechanisms that reduced fouling and provided backup capability if primary systems failed. Production challenges proved equally daunting. Boeing realized that conventional assembly line techniques could not handle the B-29's complexity. The aircraft contained 40,540 different parts and required 600,000 rivets for assembly. Each bomber needed 12 tons of aluminum sheeting, over 1,000 pounds of copper, and approximately 9 miles of internal wiring. Traditional manufacturing methods would require decades to produce the quantities demanded by military planners. The crisis reached its peak during what became known as the Battle of Kansas, at Boeing's Wichita plant in March and April 1944. Hundreds of aircraft sat incomplete on the production line, awaiting engines, electronics, or other critical components. Quality control problems caused repeated delays as inspectors rejected aircraft that failed to meet specifications. Worker inexperience contributed to manufacturing defects that required extensive rework before aircraft could be accepted by military inspectors. Boeing production engineer Oliver West developed a revolutionary multi-line assembly process specifically for the superfortress. Instead of a single assembly line, 6 parallel lines converged around 3 final assembly stations. Workers specialized in specific aircraft sections, using pushcarts, forklifts, and conveyors to transport components between stations. Overhead cranes positioned major assemblies in the final construction bay, where 4 complete aircraft were assembled simultaneously. At peak production, the Wichita plant employed 15,000 workers in 2 shifts and produced nearly 5 aircraft per day. The tragedy of February 18, 1943, nearly ended the program. Eddie Allen had been conducting engine performance tests when fuel from a defective filler cap leaked into the wing leading edge and ignited. The fire burned through critical structural components, causing wing failure and the fatal crash. Allen's death devastated Boeing and threatened to destroy military confidence in the entire project. Insurance companies refused to cover test flights. Congressional investigators questioned whether the B-29 represented sound investment of wartime resources. General Henry Arnold, commanding the Army Air Forces, made the critical decision to continue development despite the setback. Arnold understood that the Pacific War's outcome depended on America's ability to bomb Japanese industrial targets. No other aircraft under development possessed the range and payload capacity necessary for strategic bombing operations across the Pacific. Arnold assigned his deputy, General Loris Norstad, to oversee the program personally, with instructions to solve the technical problems regardless of cost or complexity. The engine problems required fundamental redesign of cooling and fuel systems. Engineers developed new carburetor configurations that provided better fuel metering under varying flight conditions. Improved cylinder head designs enhanced heat dissipation, while strengthened internal components reduced mechanical failures. Most importantly, new engine control procedures taught aircrews to manage power settings carefully to prevent overheating during critical flight phases. These modifications gradually improved reliability, though engine fires remained a constant concern throughout the war. By late 1943, B-29 aircraft began reaching operational squadrons despite ongoing technical difficulties. The 20th Air Force established training programs to prepare crews for the complex aircraft, emphasizing engine management and emergency procedures. Pilots discovered that the Superfortress flew differently from any previous bomber, requiring new techniques for high-altitude operations and formation flying. The aircraft's size and weight demanded precise control inputs and careful attention to fuel management during extended missions. Training programs revealed the aircraft's demanding flight characteristics. The high wing loading created steep approach angles that challenged pilots accustomed to conventional bombers. Stall speeds exceeded 80 miles per hour, providing minimal safety margins during landing approaches. The tricycle landing gear configuration required different ground handling techniques that maintenance crews had to learn through trial and error. Most significantly, the pressurization system introduced new physiological challenges that required specialized training for aircrew survival at extreme altitudes. Flight engineers faced the most complex training requirements due to the B-29's sophisticated systems. The aircraft featured over 100 different controls and instruments that required constant monitoring during flight operations. Engine management alone demanded understanding of cylinder head temperatures, manifold pressures, fuel mixture settings, and turbo supercharger operations across varying flight conditions. Emergency procedures for engine fires, pressurization failures, and electrical malfunctions required split-second decision-making that could determine crew survival. The first combat operations began in June 1944, with missions against Japanese targets from bases in China and India. Operation Matterhorn required B-29 aircraft to ferry supplies over the Himalayan mountains to forward bases before launching attacks against Japanese steel production facilities. The logistics proved nightmarish, with aircraft spending more time hauling fuel and spare parts than dropping bombs on enemy targets. Initial bombing results were disappointing, with high-altitude precision bombing proving ineffective against dispersed industrial targets. The China-Burma-India theater presented unique challenges that exposed the superfortress's operational limitations. Monsoon weather grounded aircraft for weeks at a time. Primitive airfield conditions caused frequent mechanical failures and landing accidents. Japanese fighter interception proved more effective than anticipated, with enemy pilots developing tactics specifically designed to exploit the B-29's vulnerabilities. Most critically, the complex logistics chain from India to forward bases in China consumed enormous resources while delivering minimal strategic impact. The strategic situation changed dramatically when American forces captured the Mariana Islands in summer 1944. Saipan, Tinian, and Guam provided air bases within range of the Japanese home islands, eliminating the complex logistics of China-based operations. The 21st Bomber Command moved to the Marianas in late 1944 and began systematic bombing campaigns against Japanese cities and industrial facilities. Major General Curtis LeMay assumed command of bomber operations in January 1945 and revolutionized B-29 tactics. LeMay abandoned high-altitude precision bombing in favor of low-level incendiary attacks against Japanese urban areas. The new tactics exploited the superfortress's defensive armament and payload capacity while avoiding the weather problems that plagued high-altitude operations. Firebombing raids using hundreds of B-29 aircraft devastated Japanese cities and crippled industrial production more effectively than conventional bombing techniques. The Tokyo raid of March 9 through 10, 1945, demonstrated the superfortress's devastating potential. 334 B-29 aircraft dropped nearly 1,700 tons of incendiary bombs on the Japanese capital, creating a firestorm that destroyed 16 square miles of the city and killed an estimated 100,000 civilians. The success validated LeMay's tactics and proved that strategic bombing could achieve decisive results when properly executed with appropriate aircraft and weapons. The Tokyo mission represented a fundamental shift in strategic bombing doctrine. LeMay ordered aircraft to attack individually rather than in formation, reducing defensive fire exposure while increasing bombing accuracy. Bombers approached at altitudes between 5,000 and 9,000 feet, well below the range of most Japanese anti-aircraft guns, but high enough to avoid small arms fire. The low-altitude approach eliminated wind drift problems that plagued high-altitude bombing, while allowing visual target identification under most weather conditions. Incendiary bomb loads consisted of clusters containing small bomblets filled with napalm and phosphorus compounds that ignited upon impact with structures. The bombs created multiple fire sources that overwhelmed Japanese firefighting capabilities and merged into uncontrollable conflagrations. Wooden construction, typical of Japanese cities, proved highly vulnerable to incendiary attack, with fires spreading rapidly through densely populated residential areas. The firestorm generated winds exceeding 100 miles per hour that made firefighting efforts impossible and trapped civilians in burning neighborhoods. However, the B-29's most significant contribution to ending World War II came through a top-secret program that began in late 1944. The Manhattan Project required an aircraft capable of delivering atomic weapons against enemy targets. The bomb's size and weight demanded special modifications to standard B-29 aircraft, creating the silver plate variant specifically designed for nuclear missions. Only 15 aircraft received these modifications, operated by the highly classified 509th Composite Group. The silver plate modifications represented a complete reconceptualization of the bomber's purpose. Standard defensive armament was removed to save weight and reduce complexity. Special shock mounts protected sensitive equipment from the anticipated blast effects. Enhanced communication systems enabled coordination with ground control stations during the critical mission phases. Most significantly, the aircraft received specialized training equipment that allowed crews to practice bomb delivery techniques without using actual nuclear weapons. The silver plate B-29 aircraft featured enlarged bomb bays to accommodate the atomic weapons, modified release mechanisms for the unique bomb shapes, and enhanced electrical systems to power the complex arming devices. Special radar equipment enabled precise navigation to targets, while additional fuel capacity extended range for the long missions anticipated. Most importantly, the aircraft received special finishes designed to reflect thermal radiation from nuclear explosions, protecting the crew during escape maneuvers. Colonel Paul Tibbets commanded the 509th Composite Group and personally selected aircraft number 44-86292 for the first atomic mission. On the morning of August 6, 1945, Tibbets ordered maintenance personnel to paint his mother's name, Enola Gay, on the aircraft's nose. At 2:45 a.m., the Enola Gay lifted off from Tinian, carrying the uranium bomb designated Little Boy, beginning the 12-hour mission that would forever change human history. The flight to Hiroshima proceeded without incident. Weaponeer Captain William Parsons armed the atomic bomb during the flight, while Assistant Morris Jepson inserted the final arming plugs 30 minutes before reaching the target. Navigator Dutch Van Kirk plotted the 1,500-mile course, while Bombardier Thomas Farabee prepared for the precision required to deliver the weapon accurately. At 8:15 a.m., from an altitude of 31,060 feet, Farabee released Little Boy over Hiroshima. The atomic explosion exceeded all expectations. The uranium bomb generated the equivalent of 15,000 tons of TNT, creating a fireball that reached temperatures of several million degrees and destroyed everything within a 2-mile radius. The mushroom cloud rose to 45,000 feet, visible to the Enola Gay crew from over 11 miles away. Tailgunner Bob Caron photographed the destruction as the aircraft escaped the blast area. An estimated 70,000 to 80,000 people died immediately, with tens of thousands more succumbing to radiation effects in following weeks. 3 days later, on August 9th, Major Charles Sweeney piloted the B-29 boxcar on the second atomic mission. The primary target was Kokura, but smoke and haze from previous conventional bombing obscured the city. After 3 unsuccessful bombing runs, while Japanese fighters climbed to intercept and anti-aircraft fire intensified, Sweeney diverted to the secondary target, Nagasaki. At 11:02 a.m., Bombardier Kermit Behan released the plutonium bomb Fat Man from 30,000 feet. The Nagasaki mission nearly ended in disaster. Boxcar's fuel transfer pump malfunctioned, creating a critical fuel shortage that threatened the crew's survival. Weather delays at the rendezvous point wasted precious fuel, while mechanical problems complicated the bombing run. Fat Man exploded with the force of 21,000 tons of TNT, destroying 44% of Nagasaki and killing an estimated 35,000 people immediately. Sweeney barely reached Okinawa with fuel exhausted, landing at an emergency field with engines stopping on the runway. The psychological impact of atomic bombing proved as devastating as the physical destruction. Emperor Hirohito announced Japan's surrender on August 15th, citing the enemy's use of a new and terrible weapon that threatened the complete destruction of Japanese civilization. The B-29 superfortress had achieved what years of conventional bombing could not accomplish, forcing Japanese surrender through the demonstration of overwhelming technological superiority. The aircraft that critics declared too heavy to fly had delivered the 2 most decisive bombing missions in human history. From the first prototype's maiden flight to victory over Japan required less than 3 years, a testament to American industrial capacity and engineering innovation under wartime pressure. The B-29 program cost over $3 billion, exceeding even the Manhattan Project's expense, but achieved strategic results that justified every dollar invested. Post-war analysis revealed the superfortress's true significance extended beyond its role in ending World War II. The aircraft established principles of strategic bombing that dominated military thinking for decades. Its pressurized crew compartments, remote gun turrets, and long-range capability became standard features of subsequent bomber designs. The complex logistics required for B-29 operations pioneered techniques later applied to intercontinental nuclear deterrence during the Cold War. The engineering achievements represented in the B-29 influenced commercial aviation development throughout the jet age. Boeing applied lessons learned from Superfortress production to civilian aircraft design, creating the Stratocruiser airliner and eventually the revolutionary 707 jet transport. The manufacturing techniques developed for B-29 assembly became standard practice for large aircraft production, enabling the massive commercial aviation industry that emerged after the war. 22 B-29 aircraft survive today, preserved in museums worldwide as monuments to the engineering genius and human sacrifice that created them. 2 aircraft, Phi and Doc, remain airworthy and continue flying at air shows, allowing modern audiences to witness the sight and sound of these legendary bombers. The Enola Gay occupies a place of honor at the Smithsonian's National Air and Space Museum, where visitors can examine the aircraft that ushered in the atomic age. The Superfortress's legacy extends beyond its technical innovations to fundamental questions about warfare and human civilization. The atomic missions demonstrated technology's power to end conflicts decisively, but also revealed warfare's potential for unprecedented destruction. The aircraft that was too heavy to fly had carried humanity into a new era, where the fate of nations could be determined by individual bombers delivering weapons of unimaginable power. That February afternoon in 1943, when Eddie Allen's burning prototype crashed into Seattle, critics believed they had witnessed the failure of American aviation's most ambitious project. Instead, they had seen the birth pangs of an aircraft that would prove decisive in the greatest conflict in human history. The B-29 Superfortress rose from the ashes of that tragedy to become the weapon that ended World War II and forever changed the relationship between technology and warfare. In just 2 missions over Japan, the aircraft that critics said could never fly had flown into legend,